All right, so let's begin by reviewing our picture. The Lie group in green is a topological group of transformations of a vector space Vn. Now, the reason I'm going back to the vector space picture is because we are now going to inquire about the matrix groups, right? We're going back to our classical groups, which were matrix groups, and we understood matrix groups to be that any element in the matrix group is a transformation on an n-dimensional vector space. So here we have our eta parameters that describe every member of this matrix group, and then each member of the matrix group can represent a change of basis in an underlying vector space. That's the way Gilmore likes to set this up. So now this guy is a matrix group, and we're going to ask ourselves about the infinitesimal generators of a matrix group. So that's what we're going to talk about today. So before we begin, let's make sure we get a good picture of our dimensionalities. The matrix, the underlying vector space will have n dimensions, and since we're dealing with matrix groups, this means that each member is going to be represented by a column vector with n elements, right? So there'll be n of those guys, which of course means that each matrix is going to be n by n. And that is going to mean that we are dealing with an n-dimensional representation. Right? That's the language we use, representation. And the reason is because this group could actually have properties that can take many different representations. For example, the orthogonal groups that we talked about, and the symplectic groups, they can be represented with as transforming totally different vector spaces, meaning different dimensional vector spaces, but it's the same underlying group. And ultimately, we'll discuss that in great detail, but right now what we need to know is that whatever the geometric space's dimension is the representation dimensionality of the underlying Lie group. But then, even more importantly than that, because the reason I say more importantly is because you can choose this sort of arbitrarily for many groups. Or any integer value of n, you can create a representation. That's not totally true. There are some groups that are missing certain representations that you cannot construct. But, for example, we saw that you had to have even dimensions for the symplectic groups, right? So all the odd ones were missing. But the underlying core dimensionality of this group is the number of parameters it takes to describe each element of the group. And that is eta, and that's reflective of the dimensionality of the topological manifold that this group actually is. Remember, this is a Lie group, so it's a eta-dimensional manifold of matrices, right? Each point in this space is a matrix, but each matrix can be mapped into Rn and R eta, and eta is the number of parameters it takes. So that basically means that if I have say I'm dealing with a three-dimensional representation, well, I have eta parameters. Let's say eta equals 2. That means I can draw every element, say alpha, can be drawn as. So each member of the group can be drawn like this, right? Each element, the 1, 1 element, is a function of 2 parameters, mu and nu. The 1, 2 element is a function of 2 parameters, mu and nu. So despite the fact that there's 9 independent points here, or 9 independent matrix elements, there's only 2 parameters. And this whole matrix can then be plotted in R2, where the mu parameter and the nu parameter are the axes of R2. And so this point in R2 represents this matrix evaluated at that value of mu and that value of nu. All right, so that's how these matrix groups are defined. That's how they fit into this bigger topological picture. This becomes a topological group of matrices because I can take this parameterization, map it onto R eta, and that mapping obeys all the rules of a manifold, which means I can do it in, I can break this up into charts, right? The charts overlap. If they overlap, I can create functions that connect the two overlap regions, or the coordinates of the two overlap regions in, of the different charts and all of that stuff. So because of that, this is now how we have to think of our group elements, right? Where the size of the matrix, right, if I call it R by R, that R is the dimensionality of the geometric space that we're dealing with, and the number of parameters is the dimensionality of the manifold that describes the group. All right, so with that in mind, how does Gilmore then describe the infinitesimal generators of such a matrix group? So let's just go right to the text. And here you see we are dealing with R by R matrices, right? So that's this size here, right? And each generator, right? And there's going to be, the index mu is on the generator, so mu is going to go from 1 to eta. And so the muth generator, the muth infinitesimal generator will be defined by this limit right here. And the limit, this expression up above, m with all the zeros in the a mu, that is to represent this guy right here, right? Let me clean this up a bit, right? So this thing here would be, for example, if I did it in the right ink, this might be m mu nu, right? That would be m mu nu. And then if I wanted to write m mu 0, I would then put a 0 in all of these slots, like that, right? And then if, and then we have to remember that m 0 0, right, would be, is supposed to be, that's the matrix from representing, that's the matrix associated with the coordinates 0 0 in the underlying space, right? See if I have that up here, right? So I take this guy, and it should map through the manifold mapping right to the origin, right? So that would mean that this guy is the identity. So M00 is supposed to be the identity matrix. And then when you understand that, you realize that you're taking the matrix where all the parameters are set to 0 except for 1. You subtract off the identity matrix, divide by the parameter that's not 0, and then take that parameter to 0. So you're essentially taking the derivative of this thing with all of the variables set to 0, all of the parameters set to 0 except 1. So you're taking the derivative with respect to just one of those parameters. And that is the that will result in a matrix, right? If you do that process, you're going to get a matrix, because from this, you're ultimately going to subtract, right, m of 0, which will be a matrix element subtraction, because matrices can be added and subtracted. And then you divide the whole thing by the parameter that you're taking the limit of, which is a term-by-term division. In fact, if that doesn't look as good to you, you could think of it as, let me see, I will erase this, and you just think of it as 1 over mu times this whole thing, like that, right? And the limit of, as mu goes to 0, will be ultimately a matrix, and it will be the generator matrix. Now, clearly you can do this eta times, because you just do this for alpha mu being in each of these slots, and you're going to get eta different generators. So they'll get one generator for every parameter that defines the underlying matrix group. So if the matrix group is parameterized by 3 elements, you'll get 3 generators. So if it's parameterized by 8 elements, you'll get 8 generators. Now this is really, before I go on to explain the next part, this is really important. In particle physics, this fact that the way these groups are parameterized and the number of parameters that it takes to create generators for these groups end up being physically important, because it tells you, like, for example, how many different particles exist, right? There's one particle for each generator, or things of that nature. So this is a very important fact to understand how these, if you're going to take this and study physics with it, understanding how these different groups are parameterized, the different classical groups are parameterized, is really, really important. And we'll do a few examples, hopefully one today even. Now, this next statement is not totally obvious, although it's not very difficult. But he wants you to understand that these generators are matrices, and the matrices themselves can be treated as a vector space. So if I come up with these eta generators, let's say I do that. Let's say I have this is matrix X1, this is matrix X2. Let's say I come up with 3 of them. This is matrix X3. Well, matrices can be added and subtracted, and they can also be multiplied. So I can multiply this by a number lambda 1, and this by a number lambda 2, and this by a number lambda 3, and I can add them together. And what will I end up with? I'll end up with another matrix, lambda mu x mu, right? This lambda mu x mu is an Einstein sum that represents this in shorthand notation. And that's exactly what he's got right here. He's got that Einstein sum. So it's a reasonable exercise for the reader to say, okay, well, if I have this as my definition of x mu, is this always going to be equal to this? But what the point is, of course, yes, the answer is yes. But the point to take away from this is that if I take a generator, multiply it by a number, and do the same for each generator and add them up, the thing I get is going to be another matrix. And in fact, that matrix can be understood as a generator in the sense that now this is the definition of this generator. In other words, if I take this limit, I'm going to end up with a linear combination of objects that were taken in this limit. And therefore, I can think of this guy, and this guy as the basis of a 3-dimensional vector space. And that's a different vector space altogether than this vector space, right? Now I'm not talking about this vector space. We kind of almost have to have another picture if we wanted to track all these spaces. Why don't we do that? So you might consider this type of picture now, right? We have our ultimate Lie group, or our core Lie group. This is sort of where we're starting from, the Lie group, right? And we develop everything around it. There's other, in physics, you tend to start here, which we'll introduce in a second. But you start with this Lie group. It's a Lie group of transformations on some underlying geometric space. And now we've calculated the generators of this Lie group using this relatively simple formula of taking these derivatives, right? This formula right here, right? We've taken that, used that formula. We found eta generators. And then what we do is we take those eta generators and we, for right now, we put them together and we create a vector space where those generators are the basis, right? These guys here are the basis of a vector space. So what does that mean? Well, that means we have to be able to add them, right? There has to be an identity element out there. There has to be a field associated with it, right? So we'll probably take the field of real numbers for this particular circumstance. And let's see. And it has to have a dimensionality, which in this case is 3. And so we've got a vector space. We've created a vector space out of these generators. Now let's be very careful. Ultimately, we get more than a vector space. Ultimately, we're going to get something called an algebra, and this will be called the Lie algebra. Right. So in order to promote from a vector space to an algebra, what we're going to need is a vector multiplication, right? We're going to have to be able to take 2 vectors, multiply them together, and get a third vector, right? Now, you might want to jump in and say, oh, well, these are matrices, right? X1 is a matrix, and X2 is a matrix, so it seems pretty obvious that if you multiply them together, you're going to get X3. And the issue, actually, though, is whether or not X3 can be written as a linear combination of, or I shouldn't say x3, maybe some other matrix, right? Some other matrix M. You want to know is, can M be written as a linear combination of x1 and x2 and x3, right? We have to check to see if matrix multiplication satisfies that property, right? There's an obvious way of multiplying matrices together, and you might think, well, that's going to be the multiplication of the algebra. But let's put that on the shelf for right now, right? Right now, let's just think of this as a vector space, understanding that eventually this is going to be the Lie algebra, and which is sort of the point of this lecture. We have to define what that thing is. We're aiming towards understanding this Lie algebra. But one thing is clear, is that the Lie algebra, or as it is now, the Lie vector space, I suppose, is bound together with the Lie group through this calculation here. And that's kind of important because they come in pairs, right? A Lie group has a Lie algebra, and a Lie algebra has, well, that's a good question. We've found a Lie group has a Lie algebra, but does a Lie algebra have a Lie group? In other words, can I always go backwards? And it turns out the answer is no, right? I could start with the generators, and I could end up in several different possible Lie group places with the same set of generators, right? And that is a subtle subject that we definitely need to dig into, but we won't do it yet today in this lecture. But the point is that we can associate with every Lie group a Lie algebra for sure. So let's just quickly run through an example using the standard example we've been doing so far, which is the one that Gilmore presents right here. Right? We start with knowing a lot. We know the parameterization of our Lie group, right? That's actually pretty big news, right? We understand how to write down every matrix in our matrix representation, our 2x2 matrix representation of our Lie group of scales and shifts that we've been doing for the past few lessons. So if I take this formula right here, right, and I set everything to 0 except one parameter, and then I take the derivative with respect to that parameter. So I'm going to set everything to 0 except for alpha 1. So everything is alpha 2. So alpha 2 becomes 0. Then I take the derivative of everything with respect to alpha 1. Let's see if I can blow this up a little bit. And I get, in this slot here, I get e to the alpha 1. This will be 0. That'll be 0. The derivative with respect to alpha 1 of 1 is 0. So all of these terms are immediately 0. And this guy here was e to the alpha 1, or I guess alpha 1. But you set all the parameters equal to 0 at the end, and what do you get? You get a 1 right there. So that is considered a infinitesimal generator of the Lie group, right? So this is this definition here. Don't complicate yourself by using the definition from the other lecture we did where we talked about the transformation of functions, right? This is a much simpler definition, actually. So then we can do the same thing and find, so that's the x1, you could have written that as x alpha 1, right? Because you're really identifying the parameter. Each of these generators gets associated with one of the parameters that builds your Lie group matrix element, or matrix, a matrix. So then for the second circumstance, you take the same matrix, but now we're going to do this whole exercise with alpha 2. So we set alpha 1 to equal 0, so that'll put a 1 right there. Then we take the derivative of everything with respect to alpha 2, and that'll turn the 1 into a 0, the 0, the 0, and the derivative of alpha 2 with respect to alpha 2, of course, is 1, and then you get this guy. So now you have the two generators. There's no third generator because there's only two parameters in the description of the Lie group. The Lie group is a two-dimensional manifold. We've gone through that. And so now, if I'm going to talk about this vector space that we've identified, that vector space is going to have two basis vectors. The first basis vector, let me increase my thickness a little bit. The first basis vector is going to be, 1, 0, 0, 0. And the second basis vector is going to be 0, hold on, I already forgot what it is. 0, 1, 0, 0. 0, 1, 0, 0. So these guys are the two basis vectors of our two-dimensional vector space for our example. So what are the elements of this two-dimensional vector space? Well, those elements are going to be things written in the form lambda 1 times x1 plus lambda 2 times x2, where lambda is an element of the underlying field, which will be the real numbers. And every single vector can be written that way, right? Now, ultimately, like I said, we have to learn how to create a multiplication. For this to become a Lie algebra, this vector space has to develop a multiplication. So we have to talk about that. But right now, there's really no need for it. Right now, we're just talking about the algebra itself. The reason there's no need for it is because every generator can be written in this form here. Every generator, this is just a basis of all possible generators. But what do we actually mean by a generator? Well, remember, going back to this, everything written in this form is considered a generator, and this is how you calculate that generator. A generator is just a generator of an infinitesimal movement inside the group, right? An infinitesimal distance away from the identity. It doesn't matter what direction. In these guys, the infinitesimal direction is in the direction of the parameter alpha. And when I say direction of the parameter alpha, what are we talking about there, right? Remember, the entire Lie group is parameterized in R squared. So every point in R squared represents an element of the Lie group. So when I say we're going to move in the alpha 1 direction, right? That's alpha 1, that's alpha 2. I guess these are superscripts, right? 1 alpha 2. So that would mean I start at the identity and I'm interested in all the Lie group elements in that direction. If I march off in the alpha 1 direction, likewise, it would be all of the Lie group elements over there. But I can march in any direction I want. And if I marched off in this direction, it would be parameterized by some number tau, and each of the alpha 1 and alpha 2 would vary with tau according to lambda 1 and lambda 2. It would just be a proportional. So any one of these things, as long as this distance ultimately is considered infinitesimal, then any one of these things would be a generator of the group. And again, it's a bit of an exercise to show that this statement here is literally the linear sum of objects like this, right? And to do that, you just have to understand we're doing differentials df dx dx plus df dy. Think in terms of this if you're going to do that proof for yourself. That ultimately, I guess you would go dc would equal this. Right? Remember this kind of definition, and that'll help you assemble this, and you use the chain rule too. So the point is that any generator can be written in this form, so it's very easy to establish these guys as the basis of a vector space, and any linear combination of them is a generator. So when we go back and we talk about what's going on in this vector space, we say it is a vector space of infinitesimal generators. Now, of course, the notion of that's really what it comes down to. So let's do a quick example which is a little more interesting than the shift and scale example. So let's consider this parameterization of a 2 by 2 matrix. This is pretty interesting because if you look at it, we have 3 parameters, A, B, and C. A, B, and C. So we know that if this is going to be a Lie group, it's going to have to map into R3, right? So this is now a 3-dimensional Lie group, right? Remember, the dimensionality of the Lie group is determined by its mapping as a manifold, right? So that's the number of parameters that describe the matrix. So clearly we have 3, and then this element here, this 4th matrix element, is just essentially a function of A, B, and C, but in principle, it's a function of these three matrix elements, which is another way of thinking about how the dimensionality, which would normally be 4 of an arbitrary matrix, gets shrunk because you're forcing it to be parameterized by 3 parameters. Okay, so what's so special about this matrix? Well, if you take its determinant, right, let's say we'll call this matrix M A, B, C, right? Hold on. Right, so M, A, B, C, this is how we will write this matrix, right? It's a function of A, B, and C, but it's a 2 by 2 matrix, right? That, if I wanted to look at the determinant of M, A, B, C, what would it equal? It would equal, actually, you know what? I've written this wrong. I can already tell I've written it wrong. The first term must be 1 plus A, right? 1 plus A. And the reason you could tell it was wrong is, remember how I said, oh, well, we want M of 0, 0, 0 to equal the identity, right? Well, if I did that, then A equals 0 would put a 0 there. So it's not the identity matrix, right? So this parameterization would not put the identity matrix at 0. So I know something's wrong right away. And what I did was I forgot to make this 1 plus A, right? Anyway, so now you can look, right? Now, if A is 0, that's 1. B is 0 and C is 0, that's 0 and 0. If A is 0, B and C are 0, then that's 1, so you get the identity. So that's perfect. Maybe I should even draw that right in here, right? The identity is at 0, 0, 0. Oh, and since this is 3 dimensions, I guess now I get to do it like that. Okay, but anyway, what's the determinant of this thing? Well, the determinant of this thing is 1 plus A times 1 plus BC over 1 plus A minus BC, which of course the 1 plus A's, they cancel, and then the BC's cancel, and you get 1. So this is this is a set of matrices whose determinant, a 2 by 2 matrices whose determinant is always equal to 1. So that is SL2R, right? This is a parameterization of the special linear group 2R. So now we can immediately ask ourselves, what are the generators of this thing? And the way we calculate the generators is using this formula right here, right? That's how we're going to calculate the generators. Once we decide the parameterization, the generators are this easy to calculate. But we started knowing a lot. Like I said, we started knowing how the Lie group itself was parameterized. So what do? Well, we take these derivatives, and let's do that. So this is the first calculation we need to do, is the partial derivative of M A00 with respect to the parameter A. So let's see, how do we do it? We set B to 0, C to 0, BC is 0. The derivative of this with respect to A in that first slot is going to be 1. And down here, in this spot, it's going to be, let's see, that's a 0, that's a 0. This will be 1 over, or minus 1 over 1 plus A quantity squared, right? And then we set everything equal to 0, and we end up with 1, 0, 0, minus 1, right? So that is what we would call XA. So I'll just put it over here in the corner, and now we will calculate XB. So this calculation is, well, it's the same thing, except now we have B, and we're taking the derivative with respect to B, and this is what that matrix looks like. Let's see if I didn't screw that up. Let me just check. Derivative of the numerator is just 1 over A. That's a constant. Derivative, it's, yeah, so that's just C over 1 plus A. Set everything to be 0. C is 0, so you end up with that as your generator for B. So I'll add that into our list. So now we have 2 of our 3 generators, and now we go back and do the third. And in this case, we now are using the derivative with respect to C, so that's 0, that term is 0, that term is 1. Then this term is B over 1 plus A, but when you set everything to be 0, the b being 0 drives that to 0, so you end up with this generator. So we'll now add that. And voila, we have our 3 generators. And this will form the basis of a vector space under matrix addition over the real numbers with scalar multiplication assigned to the real numbers. And every combination, lambda, alpha, x, alpha, that will be a generator, an infinitesimal generator of the group in a given direction. Right, so it's a given direction, away from, I guess now I have to do a 3-dimensional picture, but away from the identity in the direction A, B, C, right? And one of those, in some combination, some direction away from the origin, will always be able to be expressed as a linear combination of these 3 guys. So that is how we produce this thing that right now we're kind of calling the Lie vector space, right? Or it's really the vector space of infinitesimal generators. And we'll slowly figure out why we're going to make this into a Lie algebra. All right, so let's review what we've done and prepare ourselves for what we're going to learn next. So we really started with this definition of the generator of the infinitesimal generator of a Lie group of matrices, right? This is a matrix group we're dealing with. So because of that, if you look at what we've done is we have found what we have found is the linear approximation of the group in the vicinity of the identity. We found that first derivative of that group, the partial first derivative of that group, with respect to one of its parameters right around the identity. This is called the linearization of the Lie group. So we have linearized the Lie group such that for small divergences, small movements away from the identity, we can say that the actual Lie group element is going to be equal to the identity element of the group, right? The identity element, which I'll call m, just 0, plus some small number times a generator, whatever generator you choose. And that generator could be xa for the last example, xb, xc, or it could be lambda mu x mu. It could be some generator that is a linear combination of them. But the new Lie group element with a small displacement from the identity is going to be closely approximated by this expression. Now, it won't be exactly equal to this expression, right? Because there will be higher order terms in the generators, right? There'll be higher order terms that are being ignored. But for small infinitesimal translations, you can generate the infinitesimal Lie group element infinitesimally close to the identity by knowing these generators. Okay, so that's what this is. That's why this is called the linearization of the Lie group right at the identity. In fact, why don't I just make that point really clear right over here, right? Using this picture, let's see, using this picture right here, if this is the identity of the Lie group, right, we can, every point in this space, right, every point in this space has a, say I put this point right here. That point is a coordinate with coordinates A, B, C, the coordinates in the parameter. That represents a matrix of the Lie group that can be calculated by 1 plus A, B, C, and then 1 plus B, C over 1 plus A. I can do that calculation. I can find out exactly what that element is. But if I'm close to the identity, I can actually do that another way. I can calculate it by taking the identity itself and adding to it a small amount times the lambda mu x mu that represents this little line that connects the identity to that element. And this will almost equal that. It'll be very, very close. It'll only be missing in second order terms, which actually I think would only even inexactly fit this one. I think this is the only one that's going to have higher derivatives anyway. So this matrix element here will be a little bit off. But this is the point of why this is called the generator. It's a generator of infinitesimal translations. So in our next lesson, what we're going to show, of course, is the usual thing. If you know the infinitesimal generator, well, then if you do it an infinite number of times, I should be able to get to any Lie group element in the group itself, right? And that's going to be the subject of our next lesson. Okay, we'll see you then.